We are talking about pipe flow. It will be the last thing we talk about. I guess the one point to make, and we've made it before, is that part 3 of the class basically finishes, well, not here, finishes here. And part 4 begins here. So all by way of saying that pipe networks are not on the third midterm, it's by the same. It stops with, certainly if you looked at the review video, there's certainly 2 pipe flow questions, and there's always a dimensional analysis question. So this one is getting moderately predictable, I would say, to your benefit. So next week is online, and there are 3 classes for external flows. I guess actually it is perhaps useful to do. We have plenty of time to do the stuff I want to do today, but maybe to go back to this. It's a bit of a cluttered slide, but it does put things together for what's coming up in your career if you just look at the pictures. And so these 2 weeks have been pipe flow, where flow is driven by some pressure upstream to downstream, and it's driven by that pressure, and gravity isn't very important. Next week online it'll be external flows, calculating the terminal velocity of someone falling through the atmosphere, calculating forces that are applied on wind turbine blades would be 2 applications. It's quite similar. It's quite similar in that in this class we're looking at the drag that's applied on the fluid flowing through the pipe by the roughness and the friction on the walls. And in external flows, we're looking at the drag that's placed on an object in a flow field which is around it. The flow field may be a static air that you're falling through at 200 miles an hour, which is pretty close to terminal velocity. And you're just balancing forces again. You're balancing gravity, which is trying to accelerate a person, versus the drag forces by 2 mechanisms. And the 2 mechanisms would be shear drag by viscosity on the side, and also the kind of full frontal force acting on your chest, which is different from the force that's acting on your back, the stagnation stuff like the truck on the San Francisco airport tarmac. And so those 2 components of drag are really what we've seen here. For laminar flow, the overriding effect is viscosity, and it's the viscous drag on the side that makes the main component of force. And as velocities go up, viscosity becomes a trivial component of this, and it's the stagnation of fluid hitting the front of this closed container that is really the force. And so, not surprisingly maybe, the coefficient of drag is a bit like a friction factor, and it's typically this form. It has a form where viscosity is dominant, laminar flow, and it has a form where turbulence is dominant, and it's all due to the pressure difference between this pressure here and this pressure here. And so they all start looking the same in terms of that. And then finally, after week 13 of this semester is the week before spring break, Thanksgiving, so that'll be our midterm week. But then our course week 13 is really week 14 after Thanksgiving, and that's open channel flows. So that's flow of fluid in rivers, in ditches, in irrigation channels, whatever. Perhaps not so relevant to some of the things that you'll deal with, but maybe. You never know where your career will take you. And we'll talk about a thing called a Manning coefficient, which is really a drag frictional factor, which accounts for friction on the side of the flow, the wetted perimeter of the channel. And again, there's a laminar portion and a turbulent portion. And the reality is that since we know that the Reynolds number is a density, a velocity, and a characteristic dimension, and a viscosity, that characteristic dimension for a channel is pretty big compared to a pipe, which might be centimeter scale. An inch pipe in a house is 2 centimeters. This might be pretty wide, right? It might be 10 meters. If it's a big river like the Susquehanna, it's probably 100 meters across, I would imagine. So based on that, the Reynolds number typically is large, and it's typically all these flows are turbulent. And they're turbulent, so you end up with a single value of Manning's coefficient It's never shown as this on a graph, it's just a number. So a Manning's coefficient for a river which is, or a ditch which is concrete lined is a certain number. A Manning's coefficient for a ditch which is grass lined or soil lined is a bigger number with more drag on it. And it's typically just a single number and the reason it is a single number is because you're in the turbulent regime, and it doesn't change. And so that's kind of the big picture, if you like, of where we are, where we've come from, if you like, and also where we're going. Still with me, but not with me in person, maybe. Maybe the break will be good for both of us. I don't know. I'm still waiting to see some of you in my classroom. Red. Good. I'm still waiting to see some of you, not my classroom, in my office. So I think I've seen 3 of you have stopped by, and I've seen some of you just walking around campus. But my door is still open, so if you want to come and talk about your life and set yourself up for someone who will write a letter for you that can say more than Joe or Jane did well in a challenging course on fluid mechanics and got a grade X, which is really all I can write when asked if I don't know you, then I encourage you to stop by and say hi. My door's open most after days, and afternoons are a good time to chat. Just about nothing. I know you don't have time to waste like me, but yeah, if you wish to, do. So today we'll talk about these 2 things. We'll talk about pipe networks to close things out, and we'll talk about flow rate measurements. I'm guessing we have time to talk about both. I'll use the notes that you have. It's really pretty straightforward. As your advice, I won't draw out Bernoulli again to define exactly what that is. You know it well enough. You know that the Bernoulli energy equation is written between upstream and downstream, and we have the energy equation terms of a pump head on the left-hand side, upstream, a head loss term on the right-hand side, which is downstream, and those head losses are for major losses in pipes and minor losses around joints and fittings. And so these head loss terms, if we write it between an upstream and a downstream reservoir like this, we're really defining the head loss in terms of some head loss between upstream and downstream. And it's really, if we write it in terms of the big reservoir kind of assumptions, this head loss would be a delta Z, right, between Z1 and Z2. And so that would be implicit in this single pipe connecting these 2 reservoirs. So clearly there has to be a single head loss as we go from upstream to downstream in this particular case. And that head loss would be some amount, I guess, delta Z, right? So if we drew it in terms of 2 big reservoirs, upstream and downstream, delta H would really be this delta Z, that's all. And so as we go along this, what do we know about it? Continuity requires that the volumetric flow rate through this cross-section here is the same as this cross-section here and is the same as this. And so certainly V1A1 is equal to V2A2, and the reason for that is because the flow rates through each of them are the same. So the flow rate through here has to be the flow rate through here, and it has to be the flow rate through every section. So that means that the individual head loss terms that we have are just summed up to meet the total magnitude between A and B. So we know that on average it's going to be equal to something like, this would be the overall head loss. So this has to be the head loss in the system. And the question is, how is it divided up between these? Well, it's divided up between these because we can write these terms as being equivalent to each other. So for each one of these, we can write the individual head loss is equal to a friction factor, a length of that section multiplied by V. In this one, it would be V1 squared over 2G, and it would be diameter 1 and it'd be length 1, and we'd have to require this commitment that it has to be the same volumetric flow rate between each of these. And so between each of these components, I suppose if you just think about it in a way that makes sense, is that you'd expect that each one of these would be the head loss along here, just as you think about it, a bigger diameter pipe, much more efficient in transmitting fluid, and so the head loss in this would perhaps be less than the average. And so as you go through this, you'd expect these what it would look like would be something like this, and ultimately, so that at the end, the sum of these head losses have to equal this. So this would be the head loss between A and B has to be equal to the head loss initially, not very much. This would be, I guess, the second head loss. This would be the head loss over 2. This would be the head loss over 3, etc. And you can sum those. So, makes sense. Makes exact sense. So, I don't know whether you'll design pipes like this, but actually, for those of you working in petroleum, this is a bit like a hydraulic fracture. Don't think about this as a pipe, but think about this as a fracture being driven away from the borehole. The tip of the fracture is typically would be not zero aperture. It would dead end. And along it would be increasing apertures as you get close to the wellbore. And so it's something that is similar to what we're dealing with here. So for series flow, it has to be that the flow rates are equal to each other, and the head losses have to sum to the total head loss across the length. For parallel flow, the converse is true. This head loss here, if you write Bernoulli between the upstream and downstream in this pipe, would be this route here that goes to here. Right? And if you write Bernoulli for this equation separately, you'd end up with an equation which would also require that the head loss across the system, delta Z if you like, is the same. And so for both of these, the head loss in this flow channel and the head loss in this flow channel have to be the same. And the flow rates, therefore, will just be the summation of those. If you have 2 pipes, it would be Q1 plus Q2. If you had 10 pipes, it would just be the summation of the whole bunch of them. And so they don't differ in any regard in that. So that's pretty straightforward. Makes sense, I think. So the kinds of pipe systems we might have are series arrangement of pipes, one after the other, a parallel arrangement of pipes. It also has, bearing on if you look at flow within reservoirs, I suppose. And so if you imagine having a reservoir which comprises of a bed that has a permeability 1 and a permeability 2, which is much greater than 1, then you can imagine what you'd have if you had a pressure upstream relative to downstream. So you'd expect some flow to go through this stratum driven by this flow. You remember Darcy's law. Velocity is equal to permeability, viscosity, and the pressure gradient. You'll see this in your other classes often. This is permeability. So in this particular arrangement, the flow will go a little bit down here, but a ton of flow will go here because the velocity will be very high because this will be a large number. And so preferentially, if you look at the flow coming out of here into a bucket on the other side, there'd be a ton of flow coming out of one bed and not much on the other. And so to be able to calculate the flow across this system, if you're trying to get fluids out of your reservoir, either for water supply or for hydrocarbons, then most of the flow would occur in this. And so it's a manifestation that the flow rate is some that comes through one of them and some that comes through another one. If this happens to be a big pipe or a high permeability, then the flow rates would be that. Conversely, if you have a system that looks the same as we had before, with exactly this arrangement of permeabilities, but you're pumping it upwards by having a pressure gradient that goes upwards, then to get flow out of this bed, which is highly permeable, it has to go through this bed. And so by merely applying these pressures gradients, what would happen is that this is really efficient at getting fluid out of it. And so the pressure drop would actually look a bit more like this. And then all the pressure drop would be on the second one, which is the much more resistive to flow. And so this is a bit like this series flow. So this would be series, and this would be parallel. So you might not be working with pipe systems in what you do, but certainly you'll be worrying about these kinds of geometries. Environmental systems engineers take GSI 452, I think it is, groundwater hydrology. You'll certainly talk about this kind of behavior. So this is important for pipes, but it's also true for flow in reservoirs. And of course, the one thing that we talked about in reservoirs is that we define a hydraulic head as equal to the elevation head plus the pressure head plus the velocity head. Whoops. And flow is typically so slow in these reservoirs compared to the frictional losses which are due to permeability that this is taken as zero and ignored. And so similar, but a little bit different. All right, perhaps I'm prattling on a bit too much and going a bit too slow for you, but trying to make it relevant to what you'll see in the rest of your career. So pipe loop systems are a bit more complicated, but we can rationalize it on what we've talked about already, in that the two systems we've talked about already have been in series and in parallel. And of course, this is kind of a mixture of both of those. This would be behavior in series, one flow conduit and then another flow conduit, it happens to be two in a branch. And it's also kind of in parallel because this latter part is parallel to each other and it's splitting off from this common location. So again, you could rationalize what's going on. Maybe the easiest way to do it is to think about it in terms of Bernoulli equation, in that you can write one route through this, which would be one potential flow system, would be A to B that goes through this circuit here. And that would be this. Pressure in the upper tank, well, be zero, right, atmospheric. Pressure in the downstream tank is lower. The elevations would be different, so these two terms would exist. It would be delta Z, right? Big tank approximation, 0. Big tank approximation, 0. And then you have the head loss in this pipe here, and then the head loss in this pipe here. So we can define it. And maybe then we can also go through the system a slightly different way, in that we can then go through this circuit and then through this circuit. And again, we end up at this location as well. And this equation will be the same. Big tank approximation, surface approximation, big tank approximation. These are all zeros. We're left with the elevation difference, which is the same in both tanks, right? So this and this physically have to be the same. Because it's going through this pipe in both cases, clearly this and this have to be the same. And since there are two equations that have to meet up with this delta Z, then clearly these two terms have to be the same as each other as well. So the head loss in this has to be the same over these last two circuits. And so if you wanted to draw that picture, I suppose, I'll exaggerate it, between upstream and downstream. So this would be delta Z between upstream and downstream. If we just joined those two up to see what the average flow would be between upstream and down, obviously this should be on this line here, but this height here is delta Z, let's imagine. So what's going to happen? We'd imagine that if this is a really big pipe, then it would be more open. And so what the true behavior might be would be to this point, the drop would be something like this. And if I try and draw this, a horizontal line here, obviously, whoops, this would be HL1, this term here, right? It's the same. The drop on this circuit. And then the drop on the second circuit would be this. And so I suppose that would be HL2 equals HL3, which is really what this is. And so it's kind of a combination between each of these. So clearly the flow rate in this tube has to be Q1. The flow rate in this tube has to be Q2 and Q3. So I guess in some respects we're satisfying both requirements. Q1 has to equal Q2 plus Q3. That's our continuity requirement. And also HL2 equals HL3, this requirement here. And this makes sense because the same amount that goes in here has to come out into this tank. Of course, it's coming out in two particular streams. And so those are kind of the requirements. So this, you notice, obviously, is a mixture of the two requirements for series and parallel. So the sum of the flow rates for parallel flow is this one here, which is this. And the heads equal, I guess that the heads are equal. I guess it's more like this, isn't it? More akin to this, to parallel flow. So that's it. And so the easiest way to kind of demonstrate that is to just look at maybe two examples and talk about them at kind of high level rather than go through them in excruciating detail. I guess it's on the screen, right? And so this is a question that's asking if you have flow from tank A to tank B. Initially you have only this single conduit, a single pipe in the system, and you get a certain flow rate. If you want to boost the flow rate from A to B by 30%, in other words, change Q to be Q times 1.3 by putting in another pipe, this pipe here, how big does this pipe have to be to do that? And so that's the essence of the question. So you have flow from A to B. Originally it is at flow rate Q, which we don't know. You want it to be at flow rate 1.3 times Q, and what we don't know is how big this diameter is to be able to do that. So we have to figure out how to do that. We know that the head drop between tank A and B is 25 feet, so it's in English units. I apologize for that, but that's the way it is. And it must be turbulent, right? Because the friction factor for all the pipes is equal to 0.2 to make it tractable. So don't know what the Reynolds number is, but presumably it must be if we're using that. And so I guess there are two parts, right? The first part is to, what is Q? And so we not write Bernoulli between A and B through this circuit alone and up to there. And if you do that, we have pressure A, upstream Bernoulli, downstream Bernoulli. There isn't a pump in the system, and we have two components. Frictional losses in this circuit, frictional losses in this circuit, and those are these two components here. What do we know? Atmospheric pressure, big tank, elevation difference is going to be 25 feet between these two, which we know is this. And we have a friction factor, which I guess we know is 0.02. A good number, right? 0.1 and 0.01 is the kind of range on our Moody chart. We know the length of this circuit, 600 feet. We know the diameter. We can use this as an unknown variable, so we don't know the velocity. But we do know that the diameter of this and the diameter of this are the same. So from continuity, Q1 equals Q2, and so the velocities have to be the same. So V2 and V1 have to be equal to each other because of this, right? And so that expression ends up being the head drop, 25 feet, friction factor of 0.02, Length 1 plus length 2 is 600 plus 500 feet. Same diameters. They're the same diameters, so they're the same velocities. The only term we don't know here is the velocity, and so we can solve for that, and we get a velocity of 6 feet a second. And if we multiply that velocity times an area, we get a volumetric flow rate of 1.2 cubic feet per second. So that means we've got this. So now we want to go to the new Q is equal to 1.3 times that. So we can calculate what that would be. So it's going to be 1.2 times 1.3, which is 1.54. So this is our new Q that we have going through the system. And so now we have to look at what this circuit will look like. And there's a bit of math here, but it's better perhaps to think about physically what the characteristics are of that behavior. And that is that if you think about the behavior, it's going to be this is delta Z, right? This is our 25 feet. It's going to go from upstream to downstream, and we know that overall it's going to look like this, but we don't know what individually it will look like. We do know that this part here, if it's a nice and efficient first pipe, is perhaps going to be above this. It could be below it or above it, doesn't really matter. But we know that this amount here is going to be absolutely constrained by the fact that the head loss is going to be equal to the friction factor times length 1 divided by d1 times v1 squared over 2g. And we absolutely know this, right? Because the volumetric flow rate through this is 1.3 times the original one. So that allows us to be able to calculate v1 out of this. And so if we know v1 and everything else on the right-hand side here, we absolutely know what HL is. And so in a physical sense, we know exactly what this magnitude here is going to be, HL1. And if we know what this magnitude is going to be, we definitely know what HL2 and HL3 are going to be as well, right? Because they have to be the loss from this point. This node here can only have one pressure, or one head, and it's got to change from this to this one along this circuit, and it's got to do on this new circuit as well. And so the rest of this is to do exactly that. So we can write continuity, and that is that the flow in the first pipe has to split into two, and it has to sum to the components that go down the circuit 1 and circuit 3. And we know that the total drop along the length of the pipe has to be this drop plus the drop over the second one. So delta ZA is equal to the drop on the first part, which we know. So we know what this is. We know that this is 25 feet. We don't know what this is. But if we know what this is and we know what this is, we definitely know what this is now, right? By subtracting. We can also write for the second circuit, the one that goes along here and down through here, we can write this. The head drop is 25 feet. The head loss here is the same as this one. And therefore, we know exactly what this is as well, I guess. Question mark. We can solve for this. And so if you think of that in these terms, we have, we know what this is. We don't know what this is. We don't know what this is, but we know what this is. So in terms of solving equations, you have three equations, 1, 2, 3. You have three unknowns. You don't know what this flow rate is. You don't know what this flow rate is. And you don't know what this head drop is, and those are the only three unknowns. And so the rest of it is solving for that. So I guess if we go through it, on the top circuit, We know 25 feet. We know this head loss because we can calculate it from this term, because we know exactly what this velocity is, but we don't know what, and we know what this head loss is, but we have to define it in terms of velocity. If we know 25 feet is equal to 0.2 times this term here, which we know, then the remainder of this is the friction factor, and this, we have one equation, we only have one unknown, and we solve for V2. If we know what V2 is going through this circuit, and we know what the total velocity or volumetric flow rate is here, then we know that the flow rate we have through here is going to be the difference between Q1 minus Q2, right? Just from this equation here. So we know what Q3 is, so we know what the volumetric flow rate is, and so it's a bit more difficult because we know the volumetric flow rate, but we don't know the cross-section of this pipe, so we don't know what the velocity is. So it's a bit of a problem to get that. But certainly we can get that velocity V2. The velocity V2 comes out to be this. In the top pipe, we know what the flow rate in the top pipe is because it's just the velocity V2 times its cross-section area. We can use continuity to be able to define the flow in the pipe that we're going to add as the difference between the first pipe, which takes all the flow, and then splits up into two parts, Q2 and Q3. We know what this is from up here, and so we can calculate what the volumetric flow rate is through the bottom pipe. And then if we know what Q3 is, then we also know that this has to be equal V3 times A3. We don't know what A3 is because we've got to choose it, and therefore we have to deal with that. So now we can go back to this expression. We know this, 25 feet. We know this head loss because we've calculated it before. It's this amount here. It's controlled by this velocity here. So we know what that is. The only thing here is we don't know what this term is here. We can calculate the velocity that we'd have to have here, but we don't know what, I guess we don't know what D3 is, right? Because you have to choose that. And so we know what, and this velocity here is obviously a function of the diameter as well, right? So when we write this term here, we have to write it in terms of a velocity multiplied by whatever that diameter is. And so we end up with a diameter here that we have to solve for, and it's probably not an easy equation to solve, but it comes out as this. So I think it's the point of being able to kind of rationalize what's going on. So I don't think the minutiae of this are so important, but I think the big picture of this is probably more important. And that is for this branching network. The first part, from flow from here to here, has to be a single head loss, and you can think of it like this. And flow from here to here has to be the same head loss as you go from upstream to downstream, which is the remainder of this. And that in a composite, the flow volumetric flow through here has to be the sum of the two components through here. And so I think trying to unpick things like that is perhaps useful. I know it's probably more complicated than you want. We have 5 minutes left. I don't know whether I'll go through this. Perhaps I'll just talk in overview about this. So this is an easier pipe circuit diagram because the upstream is a single head and the downstream is a single head. And so these pipes both end up with the same head loss as they go across it. And so, believe it or not, this is a bit easier to solve than others because really you just have 3 equations. You have a continuity equation which defines that the flow rate in each component, which is then split into the 2 downstream parts, have to sum to each other or have to be equivalent to each other. And the head loss as you go from upstream to downstream has to be the sum of these 2 individual components. That's all that's saying. And so if you think about it, you end up with 3 unknowns and 3 equations. The unknowns are the downstream velocity in pipe 2, the downstream velocity in pipe 3, and the fact that the head loss over the second part of the circuit has to be the same. And so you manipulate it somehow to be able to solve 3 equations for 3 unknowns and come out with it. And so it gets complicated for that. It gets much more complicated if you have a reservoir system where instead of having the downstream reservoir being the same as the other one, in which case the heads are the same and delta Z is the same. These are different, right? This is a different elevation here to this one. And so if you do that, then you need to do the same thing. And you have to decide what the circuits are. And so the circuit in this particular case would be from high elevation to low elevation through this circuit as 1. And from high elevation to low elevation through this circuit as 2. And you can write 2 equations. So the equations would be 3 equations. The equations would be that the flow rate in the downstream pipe has to be the sum of 1 and 2, just as before. And the flow rate in each of these circuits has to satisfy Bernoulli as you go from upstream to downstream. And so if you go from A to C, you end up with Bernoulli's equation as the head loss between A to C, which is the delta Z terms, and the frictional losses in both the first leg and the third leg. Well, I've got to get my email to you announcement ready for when I get back. Likewise, the other circuit is going to be, oops, I didn't mean to do that. The other circuit will be in this one, from here to here, from B to C. Likewise, the head difference between these 2 circuits and the 2 components. The frictional losses across here, which is this, and the frictional losses across here, which is this. So if you think about it, you really have 3 equations. You have a continuity equation, which says that the flow rate in circuit in pipe 3 has to be the sum of the flow rates in here. But because they're a function of V squared, it looks a bit more messy. Actually, it's not velocities, rather. It doesn't look messy. If you write Bernoulli between A to C, you end up with the energy equation. It's messy because you have V squared terms for the velocities in pipe 1 and pipe 3. And if you write it from B to C along the green circuit, you end up with a third equation with velocity squared terms in pipe 2 and pipe 3. And so I'm not going through the rest of it, but it becomes a messy equation. But again, you're basically solving. You have 3 equations and you have 3 unknowns. Velocity 1, velocity 2, and velocity 3. It's made a bit more challenging that you can't just solve it as a simultaneous equation because this is V squared. And so you have to jump through some hoops and come out with it. And I'm not going through the rest of it. I'm going to leave it at that. So that's it. So the basic idea is that we can define these behaviors in terms of series and parallel. And I think that's probably the take-home message. And I think the best way to think about these things is in terms of head losses as they occur either in series, where it's incremental head losses add to each other as you go downstream. You know what the total head loss is, but you don't necessarily know what the incremental ones are. But if you know that the volumetric flow rate is the same in each pipe, you can calculate these absolutely and individually if you know what this is and you know what the pipe diameters are because of the friction factor term. In parallel, you know that the head drop between upstream and downstream reservoirs has to be the same in all the circuits that go across. So in other words, you can calculate the velocity in each of these if you know delta H, because you know this. If you know the friction factor and you know the geometry of the pipe, the only unknown you have is the velocity in each pipe. And if you can calculate the velocity in each pipe, you can just sum the total volumes to be able to get them. So that's it. So that's the mechanics of it. And I guess we should add some practicality to this in that in closing it for the last 2 minutes is that we didn't spend much time talking about pressure, volume flow measurement, but it's always much easier to measure volumes of flow by measuring pressure differentials than measuring volumes. So you could think about three ways that you might measure volumes. You can constrict flow in a pipe like this, and you can measure pressure upstream and downstream, and you can relate those pressures to a volumetric flow rate. And that's what's done. We talked about weirs, where you have a weir across a river and you measure the upstream and downstream levels. It's akin to doing this. And you can imagine this being an orifice meter, where you have an obstruction in a pipe and you measure the pressures. Depending on how sophisticated these orifices are, then you can calculate correction factors, which you apply to be able to get the correct flow rate. And you could imagine that these correction factors vary as a function of Reynolds number. You can have nozzles in pipes so that the transition from upstream to downstream is relatively smooth, and you measure the pressures upstream of the obstruction and downstream of the obstruction and use that to have a correction factor for this equation based on how severe that obstruction is. You see on this scale here, it goes between 1 and 0.94. So this is only a 6% error in the reading just by neglecting the geometry. So that's not a very big change, but some influence of Reynolds number. Or you can have a so-called Venturi meter, where instead of having an orifice as a plate, then the actual pipe just necks down nice and smoothly and necks back out again, and you measure the drop in pressure due to the increased velocity at this point. It has to be increased, right? Because it's the same volumetric flow rate, cross-sectional area is smaller, and therefore it has to increase. So there are three possible ways you could measure volumetric flow rates. The first one is by constricting flow and measuring the pressure difference we just talked about. The second one is by balancing forces. Measure those forces somehow and convert those into a flow rate. Or you can pour water into a bucket. We talked about the first one. The second one, balancing flow, an obvious one would be an impeller, right? You turn a little turbine as you go through a pipe. The rate at which this turbine turns is a function of the flow velocity. You measure that with a magnet as it turns around, and you measure the flow velocity. A bit like a tire gauge, you could imagine having a bead inside a tube. The cross-sectional area of the tube is larger here than it is here, and therefore the velocity of flow must be bigger here than it is here. And so since we know from F equals ma, or I guess from our, F equals velocity times velocity squared, velocity area, velocity, right? Velocity times the cross-sectional area. From conservation of momentum, the force acting on this is going to be a function of velocity, and so the height to which this little bead rises within the tube is a measure of the flow velocity that's coming past it, so you can calibrate it based on that. And it's actually no different from the equations that you'd use if you're calculating terminal velocity of a person that's dropping through the atmosphere. And the third one is volume flow meters. And so a bit more sophisticated than pouring water into a bucket. The so-called nutating flow meter is just a disc that rotates inside an annulus. This disc basically flips from up to down, and so it measures the volume of fluid that's in here, and it passes it downstream. Gas meters, these big gray boxes that you see outside apartment buildings or terraced houses that are individual units, based on the idea that it basically takes a volume and it physically acts as bellows to be able to move the volume of a valuable commodity, natural gas. So you measure it quite accurately. As you fill up a bladder, the bladder moves and it exits to a downstream portion, and it just measures it by changing the volume, basically like filling a bucket of water. And so you can measure things in that way. And so three methods. Either measure pressures by constricting flow, and that gives you a flow rate. Balance of momentum, either with an impeller or with a bead, like in a tire. A tire gauge works on the same principle, or by measuring flow volumes into a volume. So I don't think you have it now, but it used to be when you bought gas, There used to be a little four-leafed thing that used to spin within the flow. You used to be able to see it as it metered into your car. And same principle as this. A given volume in something you twist around. I know you're excited to get to your next class.
No, I'm not.
With Labisha? Oh, sure you are. Well, it's been a joy. Maybe I'll see you in the rest of your careers. Maybe not. My door is always open if you're in Hosler. It certainly seems like a dead zone in Hosler these days. I think there's no one around these days. There are almost no professors around, it seems to me, which is, I think, kind of curious. But anyway, so if you're around, drop by, have a chat, and if not, good luck. Enjoy the classes online at double speed next week. Enjoy your midterm. Show us exactly what you know in the following week. You know what the questions are. 2 on pipe flow and 1 on dimensional analysis. Stand back from them. Think in terms of big pictures, I think, for each of them. That's not a hidden message in any way, but as I say, the questions are much more formulaic as we go downstream, down through the class. And so I think scores do tend to go up. So if that's a concern for you, you can perhaps take stock and take heart from that. And then then it's spring break. I guess on the Sunday of Thanksgiving, before Thanksgiving, your projects are probably due. You can probably strong arm Jai to change that if you need to. I think also on that Sunday, your assignments there's no assignment. I guess there's an assignment for week 12. Yeah, there's been an assignment due, I guess, then as well. And so there'll be an assignment due next Thursday for this week. There'll be an assignment due the following Sunday after the midterms, delayed because of the midterms for week 12 stuff after week 13. Midterms in week 13, Thanksgiving, and then after you come back, there's 1 week of classes online, which is week 13 on open channel flow, and then a midterm on the Friday, and then on the Monday, Tuesday of the last week. Again, with the idea that there isn't more than 10% of the grade on stuff that's in the week before finals. So, not that I usually go by the rules, but I think that's a good rule that protects students. So. That's it. Sorry, I don't know what else. So anyway, enjoy your rest of your careers on campus. Good luck in week 13. I'm around for the next 2 weeks, and I'm around the 2 weeks after that before the winter break. And so good luck. Been a pleasure having you. Cover up that red shirt with that black jacket. We don't want to have those showing on campus. And if I see you on campus, say hi.
All right.
Okay? Good luck. Great.